So, what do we have today? Today, we're talking about metallic bonding. I did attempt to print the study sheet for this, but it did not work out. So, the good news is it's posted to Google Classroom. It's really only one sheet, so I'll pop it up on the board when I'm done lecturing, and you can have it up there. This is not too difficult. It's a very easy concept, but we're dealing with metallic bonding. So we've already talked about ionic bonding and covalent bonding. Remember, ionic is between a metal and a nonmetal. Covalent is between two nonmetals. And now the thing we've been missing, what's between two metals? It's called metallic bonding. Easy names. And so the concept that we have here is the electron C model. And then we're going to talk about the metallic properties that we have, the names for those and kind of what they mean. So we've already kind of covered the topic that your metals, especially your metals in the middle, in the pink and in the light blue, have different numbers of charges. They can be a +2, they can be a +3. It just depends. And that's basically because you can't know in these middle metals how many electrons they have in that outer shell. They might have 2, they might have 3, they might have 4 or 5. It just depends on where they're at and kind of what they've been interacting with. And so trying to get those down to a specific charge is very difficult. Now we're going to kind of see why that is. Because metals have the ability to move their electrons around very, very easily. And so saying, this specific atom of metal has this many electrons doesn't always work out for you every single time. So metals have a unique way of bonding with each other. They have low ionization energies, which means it doesn't cost very much energy for them to lose an electron and become an ion. And so very easily they lose electrons to become positive ions. So metals lose electrons relatively easily. Empty valence orbitals of neighboring atoms overlap. And this is kind of important. So when I have an atom, let me take this with me. When I have atoms of metal, let me go ahead and mention this before I forget. No, you don't have to. It's not for everybody. I don't even know if we're going to do anything this year. We might just have a practice meet and that's it. But if you're interested in the UIL science team, if you're interested in getting to UIL, or you happen to like science, you're just interested to see what's going on. I am the UIL science team coach. I have been since I started here. It's a pretty easy competition. You just go. This is going to sound like torture to most of you. You go and you literally take a science test. I think it's 60 questions, which sounds like a lot, but you don't have to do any ones that you don't want to do. You just go through it. Whatever questions you know, you try to answer. If you don't know it, or you're like, I have no idea what this is, don't answer it. It's not going to count against you. So whatever you try counts. Whatever you don't try doesn't count. There's 3 sections. You've all taken biology already, assuming some vast error hasn't been made in your plan to graduate. So you've already taken biology. You're halfway through chemistry. I don't think anybody's taken physics. Every once in a while, I've had like a senior that's already taken physics. But if you've already taken physics, that's a bonus because most of the people that compete on the UIL science have not taken physics. And so if you can answer any physics questions at all, that will usually put you towards the top of the group. That being said, you can also advance to like regionals or state on the best biology or the best chemistry score. So you don't have to be good at all 3. You can just be good at 1 or 2 and still do pretty decent. It looks good on your college applications if you're planning on going to college. I don't know if any like hiring people for a job application will really care about it, but it's not bad. It's fun. I got a couple people coming back from last year, but really, I don't know how this is going to go. It might be all virtual. So we used to be able, if you go to regionals, we used to be able to miss a day of school because you're going to regionals during the week. But I don't know how that's going to work out this year. We might just practice and not actually do anything. But if you're interested in it, let me know. Come in during activity period after class. Shoot me an email, and I'll get you on the list and get you like a little practice test to look at. And if you're just somewhat interested, let me know. You can look at it, and if at any point in time you decide, I don't want to do this, you don't have to do it. It's not a big deal. You're not like writing a contract or anything. So back to metals. Sorry about that. What they're talking about with the overlapping valence shell, I have atoms, right? I got each of these atoms. These are like the nuclei. Let's put it in here for nuclei. And you've got your electrons like around the outside. I know they're not in orbitals, but let's just pretend they're in orbitals. And you got a couple electrons here and there. What they're saying is the orbitals in a block of metal, your outermost orbitals, maybe even the one underneath it, they're going to overlap. And so if I have electrons just kind of out here in all these orbitals, and they're all overlapping, if I have like an electron here or here, which atom does it really belong to? Is it in this atom's orbital or is it in that atom's orbital? If they're occupying the same space, it's not like you can just say for certain this atom has 5 electrons in the valence shell and this one has 5 and that one has 5. One of them might have less. It might change. Like from 1 second to the next, it might actually change. And so that is what metals do and what gives them their amazing special properties, because obviously metals act like nothing else on Earth. Metals have their own kind of qualities and things that they do. So the way that we describe this is called the electron C model. And this spelling of C is like what? What are they referring to here?
The ocean.
The ocean, yeah, the ocean. And so in the ocean, is it easy for you to see where any one like molecule of water is in the ocean? No, it's all just a big group. And one water molecule is as good as any other one. That's the same thing in like a block of metal. And I should have a block of metal, but whatever. This works, a little piece of metal. Same thing, a little piece of metal. I have millions and millions and millions of atoms in this little piece of metal. And in it, they're all just kind of sharing electrons. The electrons can move freely from one atom to the next atom and then back again. They don't have to go in a certain direction. They don't have to move at all if they don't want to. But they all just kind of share all the electrons together. And that is the electron C model. So it says the model that explains metallic bonding in which a sea of delocalized, which means the electrons that can move around or that belong to maybe 2 different atoms. Delocalized electrons move freely between metal atoms, empty valence orbitals, which happen to overlap. So because they overlap and there's empty spaces, because they're not noble gases, they don't have all 8 spaces filled up, they got empty spaces. And because they overlap, they can move around from atom to atom wherever they want to go. So those are called your delocalized electrons. They don't have a specific place. They're not for a specific atom. They just move around and go where they need to go, where they want to go. And what that results in is metallic bonding. This is the bonding between 2 metal atoms. There's an electrostatic attraction between those delocalized electrons and the metal cations that causes metal atoms to be held together. So can I like tear this apart if I want to?
No.
Yeah, well, I mean, I'd have to be super strong. But yeah, I could like bend it and break it and it'd come apart. Don't do it, but yeah, you can like let's use something softer then. You don't like trust my strength. Can I break like a paper clip?
Yeah.
Yes, I can bend a paper clip where it doesn't break, but if I put enough force into it and kind of pry it apart a little bit, I can break it. And so it's not like a difficult thing to break metallic bonds most of the time because it's just that electrostatic attraction. It's not like an actual covalent bond connecting the 2 atoms. It's just an attraction between your negative electrons and your positive nuclei, your positive cation. So here's their example here. I think this is going to be a video. If it'll play. Maybe, maybe not. I guess no. Oh, it says cannot play, unavailable. Anyways, what you would see if this video did play is the little electrons just kind of moving around randomly from atom to atom, which is what happens in a metal. So that's your electron C model, visualized or not visualized because the video didn't work. Many properties of the metals can be explained by the electron C model. For instance, conductivity. What do metals conduct?
Electricity.
What else do they conduct?
Heat.
Heat and electricity. Why do they do that better than every other material? Or depends on the metal. Why do some metals do it better than every other material? because they have those free electrons. Those electrons allow that energy to be transferred in a quick and efficient way. Ductile and malleable, what does that mean?
They're bendable.
They're bendable. Specifically now we're getting a little bit higher in school. We got to know the difference between these. One of them is pulled into wires. The other one is hammered into flat sheets. How you remember these, or how I remember these, this is kind of dumb, but it works every time. Ductile sounds like what word? Duct tape. Yes, duct tape, right? Ductile, duct tape. Does everybody see it? It's kind of close. I mean, it's not rhyming. I'm not trying to say you like make lyrics out of it. But ductile, duct tape. Is everybody good with that? So you shouldn't use it. You should use electrical tape, but I can duct tape wires, right? So the ability to be pulled as a metal, pulled out into thin wires is ductility. That's what that describes, the ability to be pulled out into thin wires. Malleability is the ability to take a piece of metal and hammer it, smash it down into a flat sheet. Malleable, for my band people, sounds like what word? Mallet, which is essentially a hammer, right? And so malleable, mallet, hammer, hammered into thin sheets. Ductile, duct tape. I duct tape wires, pulled out into thin wires. Has everybody got that a little bit? So that's how you remember the difference between these two. You will need to know the difference between these two. And then what is luster? Yes, it's the shininess. Are metals shiny in a way that nothing else is shiny? Yeah. I mean, glass is shiny, but do you ever confuse glass and metal? No. And like wood or like bricks, they're not shiny. And so metal has its own shine to it because literally when you get into the physics of it, it's taking in that light and kind of like rearranging it in a way and sending it back out looking different. It's not just reflecting all the light. Some of it's actually being changed because of the electrons in the metal. Huh? What? Diamonds are more glassy, shiny. They're a non-metal. It's carbon, and so that kind of shiny is still referred to as luster, but a metallic luster looks different than any other kind of thing. So remember, non-metals don't have these properties. Non-metals are not shiny. At least they don't have a metallic luster. They're not conductive electricity or heat. They're not ductile or malleable. Can I bend or flatten out a diamond? Nah, it's just going to break. Same thing with pretty much anything. Unless it's a metal, you don't really have that ductility or malleability unless it's in a weird state. Metals have excellent thermal and electrical conductivity, which is why we use them for so many things. They go through the malleable and the ductile. Notice malleable, hammered into thin sheets, ductile, drawn into a thin wire. And then they just have an illustration of how you kind of get this with metals. This is a little bit exaggerated because if I hit the corner of a metal block that was this thick, the bottom wouldn't poke out. But if you imagine it like as a sheet, maybe like 30, 40 atoms thick, if I hammer this thing, is there going to be a dent on the other side? Yes, and the reason is because there's no like solid bond between all these. It's just those delocalized electrons that kind of float around in the sea. If I hit one atom, it's allowed to move relative to the other atom, but still maintain that connection. So it can move, but not break. That allows you to get the bending and the pulling of metals that you can't really do with other atoms. And so you can see when they hit the corner here, everything slides down. There's no like, it doesn't break off completely. It just moves position a little bit, which is what allows it to be malleable and ductile.
So you're saying that football term came from metal?
What football term?
The old bend but not break?
I mean, I don't know that it came from metal, but yeah. But I don't know because you're not really gonna break metal. I guess you can break metal. I said that earlier, but yeah, it goes with all sorts of things. Like a stick would probably be better. A tree in a storm is probably where it came from. You bend, but you don't break. You know, I don't know that it was metal workers that crossed over into the football field and were like, we got to get this saying going. So your luster is your shininess. Specifically, if you take geology or earth and space, we'll talk about metallic luster. It's kind of its own shininess. Let's see. So the reason why metals are so shiny in a different way than everything else, when the light hits that sea of electrons, it's actually absorbed. Not all of it. Metals do reflect some light, but some of it is absorbed. The energy enters the electrons and makes them go into an excited state, and then immediately they go back to their normal state and release that energy in the form of light. So metals literally absorb the light, change it a little bit, and then spit it back out, which is why shiny metals look like no other shiny object that's a non-metal. They just have a different shine. It's almost hard to describe, like, what's the difference between a metal shine and like a diamond shine. I don't know, it looks like a metal. If you've ever seen a metal, you know they look different. That's why, because it literally changes the light and spits it back out. And so when you see a shiny metal, it's different than any other kind of shine. So that's it. There's only 8 questions. It should be pretty easy today. I will pull up the study sheet. And if you have any questions, please let me know. Where are we at? Chapter 6. And this is the end of chapter 6. Tomorrow you will take the quiz over this. And I will leave the study sheets here and write a note for him that y'all can get some study sheets. So if you'd like to use the study sheet in the quiz tomorrow, it'll be available to you. If you want to use it today, it is on Google Classroom. So just hop on to Google Classroom, and the post today has the study sheet in it. That's not what I meant to click on. Mr. Barrett. Yeah, Mr. Barrett's good, so. Okay, so there you go. Can zoom in a little bit on that. If you have questions, let me know.